So next topic is wedge friction. So in the figure you can see a body is actually lifted by another wedge. So a wedge is usually of a triangular or trapezoidal in cross section. It is generally used for slight adjustments in the position of a body. That is for tightening the fits or keys in the shaft. Sometimes a wedge can also be used for lifting the weight as shown here. The weight of the wedge is very small compared to the weight lifted. Hence, generally the weight of the wedge can be neglected in the analysis. Problems on wedges are basically the problems of equilibrium on inclined plane. So always the wedge will be having a inclined surface. So normally the body will be analyzed for an inclined surface. Thus these problems may be solved either by the equilibrium method or by applying the Lamy theorem. See that directly in the problem, find the horizontal force P on the 10-degree wedge shown in figure to raise the 1500 Newton load. The coefficient of friction is 0.3 at all contact surfaces. So the contact surfaces which comes in this problem are between the body and the wedge, and also uh, between the body and the left side surface, and also between the wedge and the bottom surface. So we will resolve the various forces acting on the entire system. So considering the equilibrium and free body diagram of the body of weighing 1500 Newton, we have equilibrium of the load of 1500 Newton, and we can resolve the forces horizontally. So when you draw the free body diagram, here there will be reaction from the board, there will be a reaction from the wedge, and there will be weight of the body, and also the frictional force between the body and the wedge. So those forces are here, and we have the F1, which is the friction between body and the wall, F2 friction between body and the wedge, and the R1 is the reaction from the wall, and R2 is the reaction from the wedge onto the body. So the angles are also given in the problem. So we are putting this, and we know that the coefficient of friction is 0.3 in all the cases. So F1 is equal to 0.3 into R1, and F2 is equal to 0.3 into R2. So resolving the forces in horizontal direction, we have R1 horizontal minus a 0.3 R2 cos 10. This minus 0.3 R2 is actually parallel to the platform, and it is resolved, or it is shifted to the horizontal axis. So cos 10 is coming into play, minus R2 sine 10. So this component of this reaction in the horizontal direction. So this and friction will be acting opposite to the reaction R1 to get R1 is equal to 0.47 R2. And on the resolving the forces vertical direction, we have R2 cos 10, which is the vertical component of this R2, minus 0.3 into R2 sine 10. So this one, friction component vertical, minus 1500 is the weight of the body, and minus 0.3 R1 is the friction value, which is in line with the, or in direction with the weight of the body. Get R2 is equal to 1894.63 Newton. Then coming to the equilibrium of the wedge. So please note that we are actually starting with the free body which is having minimum quantity of forces, right? And also we know that the load of board is coming on to the wedge. So the wedge can be treated as the PD2 and it can be analyzed. So considering the equilibrium of the wedge, similarly we have the friction force between body and the wedge, friction force between the wedge and the bottom surface, and we should find the p value required to lift the body, and R2 is the same reaction in the same direction, same line but opposite direction to the previous R2, and R3 being a horizontal surface directly perpendicular, or the various forces coming on to the wedge. So resolving it in a vertical direction, we have R3 here plus zero point 0.3 into R2 sine 10. So we have zero point 0.3 into R2 sine 10 is actually the frictional force in horizontal in vertical direction, and R2 cos 10. So this one component, this is actually perpendicular to the plane, considering it to this direction. So cos 10, we're getting R3 is equal to 1767.15 Newton, and resolving the forces in horizontal direction, we have zero point 0.3 into R2 cos 10 frictional force plus R2 into sine 10 component of this reaction, and plus zero point 0.3 into R3 which is the frictional force F3, and minus P, the external force, equal to 0, which will give you that P is equal to 1418.90 Newton. The another way of solving the problem is using the Lamy's theorem. For that, we have to consider the equilibrium of the block, and we know that the tan phi is equal to zero point 0.3 based on the previous derivation for the coefficient of friction, and for that phi, for that value zero point 0.3 equal to tan phi, we have phi is equal to 16.699 degree. Okay, in by the way of Lamar's theorem, we are considering the equilibrium of block first, with the weight of the body acting downwards. The wedge is actually lifting the body, so the body is moving in up, and we have the phi is equal to 16.699. This is the angle between reaction and the horizontal. R2 we have the reaction from the wedge, and we have the different angular values. So we can consider the as all the forces are passing through a common point. By using the Lamy's theorem, we have 1500 divided by sine 1642 plus 90 plus 2642. So 1500 by 133 degree 24 minute is equal to R2 divided by 73 degree 18 minutes. So because this is actually 90 in total, minus 16.69 and give you the value. So R2 is equal to 1977 directly by the Lamy's theorem. Consider the equilibrium of the wedge. We have the wedge here, and the R2 is the reaction between support contact reaction between the block and the wedge. We know that the wedge has to be moved left so that it will lift the body. We have the P here, R3 here, and R2, and all the angles are properly shown. Consider the equilibrium of the wedge. The wedge is in equilibrium under the forces F, R2 and R3. And by using the Lamy's theorem, we have P divided by this internal angle, that is 180 degree minus 26 degree 42 minute and 16 degree 42 minute, will give you that R2 by this angle is sine 90 plus 16 degree 42 minute. Hence we have the value of P is equal to 1417.7, which is obtained with a small, very slight variation with the previous method of solution. So coming to the next problem, two edges A and B are used to raise another block C weighing 1000 Newton as shown in the figure. Assume coefficient of friction as 0.25 for all the surfaces and determine the value of the P for impending upwards the motion of blocks. So here we have two edges compared to the previous one of single wedge, and this both the wedges are actually pushed inwards so that the block C is uh, proxy starts to move upward, and the angles are given. So first we can draw the freeboard diagram of body 1. Let's note a similarity that the wedge A and B are symmetrical with respect to the central axis. Here, coming to the body C, we have two inclined surfaces, and the coefficient of friction is 0.25 for all surfaces. So between the body C and A, we have 0.25 R. Between the body C and B, we have 0.25 R, and the reactions are actually perpendicular to the inclined surface, and it is shown here. And we have for the wedge, so this is actually the wedge A, the force P, the reaction R1. 0.25 in R1 is the reaction between the object A and the surface. 0.25 R, it is between the C and A. Please note this was the force, pressure force acting downwards. So to counter that in negative direction, this upward direction, we have 0.25 R. The reaction from the C onto the A. So all those forces are listed for the free body diagram. Then the because of symmetry, the reaction and the contact surfaces between A and C will be 1000 Newton, same as that of the B and C. And let this reaction be R. So this is actually the total system having the A and B similar, or they are same symmetric to the central axis. Considering the equilibrium of block C, this is the topmost one, and resolving the forces or vertically, we have R cos 30. So we have for the object one, see, r cos 30 plus r cos 30, because from A and B we have the reaction, minus 1000, the weight of the C, minus 2 times 0.25 into r sine 30, which is from both the surfaces left and right. So the reaction is equal to 674.74 kilonewton, sorry, Newton. And assuming the equilibrium of the wedge A, we have to resolve the forces vertically. So we have R1, the reaction from the surface, bottom surface, R1 plus 0.25 into R sine 30, so resolving the force, minus R cos component to make it vertical is equal to 0 R. So we get the R1 is equal to 500 Newton, and resolving the forces in horizontal direction, we have the P acting towards the right, P minus 0.25 into R1, then the component of 0.25 R cos 30 towards left, and also minus R sin 30 towards the left, which give you that the P required is 608.46 Newton. We can also solve this problem by the Lamy's theorem. So coming to that, we have the total system here with 1000 Newton is the force acting downwards, and we have the body A and B, the direction of motion. Mu is given as 0.25, the phi is equal to 14 degree. By using the Lamy's theorem, we have 1000 divided by sine, so this angle total 2 into 14 plus 30 is equal to Ri is actually this value. Ra and Rb are here. This is actually a refined figure, 1000 Ra Rb. So we have 14 plus 30 for single angle with respect to the vertical, and 2 times will give you the total angle, 1000 by total sine 2 into 14 plus 30 is equal to Ra by this angle. So it is 90 plus 19 minus 40 minus 30, right, is equal to Rb minus Rb divided by the same value. And on solving, we get Ri and Rb as 695.08. And on considering the equilibrium of the wedge, we have different forces coming to the wedge, including the Ra, P, and the reaction. Hence, the P divided by this total angle by sine 180 degree minus 144 and 14 is equal to the Ra divided by sine this total angle 90 plus 14, which will give you the P is equal to 608.14. 608.14, slightly different from the method of free body diagram. So hence solved. The other type of problem is the ladder friction. So this is a common problem which we encounter on climbing a height. So we have the ladder placed like this from A to B, so that the person at A can climb to this ladder and reach the point B. So the weight of the ladder is given by weight, the L by 2, L by 2, assuming the weight is acting exactly at the center, and we have a reaction from the wall Rw. Mu W Rw is the friction between the wall and the ladder. Mu F Rf is the friction between the ladder and the base, and Rf is the reaction at the bottommost points. These are the frictional and various forces acting on the ladder. So the ladder AB with the end A on the ground and end B on the wall. The ladder exerts a force on the wall and Rw is reaction on the ladder. Similarly, ladder exerts a force on the ground and Rf is that value. It's just an explanation of this figure. The upper end B of the ladder tends to slip downwards and henceforth the friction will be vertically upwards. So actually upon climbing this ladder, the ladder will try to move down, hence the friction is moving up. Similarly, upon climbing there is tendency that the ladder may slide towards the left, so that we have the frictional force. The lower end tends to move away from the wall and hence the direction of the friction force is also towards the wall. For equilibrium of ladder, the algebraic sum of vertical forces and algebraic sum of horizontal forces must be zero. Also, the sum of the moments of all the forces about any point must be zero for the limiting equilibrium. So, considering this ladder, sigma h equal to 0, mu of Rf and also this RWR in the horizontal direction is equal to 0. Vertical Rf then plus a mu W Rw is equal to W, and also we have the moment equilibrium, that is W into half largely the L by 2 cos theta. So we're taking the moment about the base, W into L by 2 cos theta minus mu W Rw into L cos theta from here to here, L cos theta minus Rw into L sin theta. So taking moment about A, we get the moment equation. And upon solving these three equations, we will get the required unknowns like the Rf, Rw, etc. Consider this problem. We have a uniform ladder 6 meter long and its weight is 300 Newton. Is resting against a wall with which it makes an angle of 30 degrees. Here angle is 30. A man weighing 750 Newton climbs up the ladder. At what position along the ladder from the bottom end does the ladder slips? The coefficient of friction for both the wall and the ground with the ladder is zero point 0.2. These are the given values. Considering the limiting equilibrium of the ladder, we have sigma Fh is equal to 0. This is the previous equation which we discussed. So 0.2 into Rf is equal to Rw. Sigma F is equal to 0. Uh, on that we get directly that Rw is equal to 201.9, because we have one equation with R of Rw and second equation with R of Rw. So we have two equation, two unknown, solving Rw. And sigma moment about A we're taking as like previous, and on that condition we can find the distance x required to disturb the equilibrium, which is x is equal to 1.92, which is the required answer for the problem. We have one more problem, that a uniform ladder 3 meter long, here 1.5, half the length 1.5. It is placed against the vertical wall, which makes an angle 30 degrees. So this angle is 30. The coefficient of friction between the wall and the ladder is 0.25, and between the floor and ladder, here is 0.35, here is 0.25. The ladder, in addition to its own weight, has to support 1000 at its top end. So maybe the man has climbed up to this point, that the weight of 1000 is assumed to be constant at the topmost point. Find the horizontal force P to be applied to the ladder at the floor level to prevent slipping. So maybe in real cases, some will put some force at the bottom to make the uh, ladder stable, right? So we need to find that force. If the force P is not applied, what should be the minimum inclination of the ladder with the horizontal, so that there is no slipping for it with the load at top end? So two way we can make this condition stable, either by applying a force at the bottom or by changing the inclination of the ladder. So we are supposed to do by both way. In case one of applying a force P, same, we can use the previous equilibrium equations to find the value. That is, consider the inclination is given as 60 degree. Sigma FB is equal to 0. We have addition force is actually 1200 downwards, and we have RF and 0.25 RW acting upwards. So FB, FH also there, P plus 0.35 RF minus RW is equal to 0. So we have two unknowns in equation 1 and three unknowns in equation 2, which cannot be solved directly. Taking moment about a equal to 0, we have 200 into 1.5 cos 60, the moment of this load, 1000 into 3 cos 60, the moment of 1000, minus 0.25 into RW into 3 cos 60, the force moment from this frictional force, and Rw into 3 sin 60 is equal to 0. So getting Rw directly from the equation 3, and then we can apply into the equation 1 to get Rf, and we can solve for the extra P required for making the ladder shape. In case 2, this theta is unknown to you, or this theta has to be changed to make this ladder shape. So in initial way, we have the given theta was 60 degree, and we need a pull off or push off 183 to make this ladder safe. So by actually increasing the angle, we can make it more safe. So we want to find the angle for that. So case 2, vertical force is equal to 0, sigma F is equal to 0, RF minus 200, RF is here, 200 is here, minus 1000, then the frictional force is equal to 0, sigma FH is equal to 0, this horizontal force at this point 35 RF, and we have the RW, and if we can solve RF and RW, then taking the moment about A equal to 0, on that we have the unknown parameter as theta, which can be solved, and the obtained value 68 degree, 68.33 degree as a safe inclination, so that no external forces are required to make the ladder safe.